Yeah, thank you very much. Do you hear me? Okay, very good. So Hardy gave a very nice introduction into exchange correlation functionals and beyond. So many-body perturbation theory and Green's function theory. And so I will build on that in the description, in terms of the description of van der Waals interactions. So you can ask the question of why we should address van der Waals interactions separately from the general question of describing exchanging correlations in real systems. And the fact is that in the 20th century, so before the 2000s, most people thought that van der Waals interactions are kind of important only in very selected systems, such as noble gas crystals and clusters. But since the turn of the 21st century, I think we have accumulated more and more knowledge about the role of van der Waals interactions in realistic systems, nanostructured systems, surfaces, biomolecules, and so on. And today it is accepted that van der Waals interactions play a crucial role in a wide range of molecules and materials, and therefore van der Waals interactions really deserve their own let's say chapter in this book or in this workshop, and I will try to convince you throughout my talk that in fact van der Waals interactions are quite important in many systems, and also it is difficult to treat them accurately, but there are approaches nowadays that allow you an accurate treatment of van der Waals interactions in a wide range of systems. So van der Waals interactions are special because they are part of long-range electron correlation energy. And long-range electron correlation energy is a very small part of your total electronic energy of your system. It is less than 0.01% of the total energy. And so just based on perturbation theory, one could say that this should be a negligible part of the energy. Nevertheless, I will demonstrate that often it is the dominant part that dictates the structure, dynamics, and properties of many real-life systems that we see every day. But because it is an interaction that essentially scales at large distances and involves many electrons, so you can compare this, for example, to what Hardy has been talking about, which is mainly short-range interactions between a few electrons, such as covalent bonds. So that really makes van der Waals interactions stand out because it involves thousands or tens of thousands of electrons over very large spatial scales, so tens to hundreds of nanometers. And so treating this practically is very difficult. Hardy mentioned the oxygen atom, right, with its essentially 8 electrons. That would be an exponentially scaling problem even if you want to store the wave function of an oxygen atom. Now imagine storing a wave function of a whole protein, including the van der Waals interactions. This is hard. And so because of that, we cannot really solve the Schrödinger equation exactly to obtain an accurate description of van der Waals interactions, but we need to think about more practical approaches. And so my focus will be on practical approaches to van der Waals interactions without sacrificing insight. So I will demonstrate how we can still keep insight and the correct quantum mechanics, yet make our approaches practical to be applicable to realistic systems of interest to you and to me. So van der Waals interactions are important throughout physics, chemistry, and biology. For example, they're crucial if you want to get the correct secondary and tertiary structure of proteins, if you want to understand interactions between nano objects such as nanotubes, if you want to understand why polymers form such intrinsically entangled structures, and why molecules, for example, wet surfaces and form interesting nanoscale self-assembled objects on surfaces. All of these effects, all of these phenomena involve van der Waals interactions. Now, van der Waals interactions also propagate to mesoscale and to macroscale, and to demonstrate this, here is a poster child for van der Waals interactions. This is so-called gecko animal that has been proven to actually walk on walls and ceilings due to the action of van der Waals interactions. So in a way, it defies gravity by using van der Waals interactions to its advantage. Now, I like to use this quote from Mark Rutner to also emphasize the importance of van der Waals interactions in chemistry and material science. So Mark Rutner is a prominent computational chemist at Northwestern University, and in 2004 he said that chemistry of the 20th century was about intramolecular interactions. So this means essentially covalent bonds, covalent reactions. But chemistry of the 21st century will be about intermolecular interactions. And this is due to the fact that non-covalent intermolecular interactions are really much more flexible than covalent interactions. They involve structures over much larger spatial scales. They involve many more electrons, and they give you much more flexibility to control intermolecular binding. And so I can even extend this quote not only from chemistry, but also to material science, nanotechnology, physics, and so on. Now, we typically think about van der Waals interactions at the atomistic scale. So we think about 2 nanotubes binding, for example. But the question is whether it's important for realistic macro-scale phenomena as well. And so here is one recent example, actually, of the fact that van der Waals interactions might be important even for macro-scale objects such as asteroids. So in this particular paper and a few papers before, actually, people have done astronomical measurements of rotational accelerations of so-called rubble pile asteroids. These are soft objects, so essentially they collect garbage from space and they grow in this way. And so people know the density of these objects and the mass of those objects, and so they can construct models for cohesive forces within the asteroid. And if you construct a classical model, which includes electrostatics, friction, and self-gravitational forces within this asteroid, essentially would predict that the asteroid would decompose instantaneously. So you cannot account for the observed rotational acceleration of this asteroid, which is quite large. And the only way to actually account for the astronomical observations is assume that there is at least 40% contribution to the cohesion in the asteroid due to van der Waals interactions. And that's the only explanation that people have found so far in order to explain the stability, the intrinsic stability of this large macroscopic objects. So I hope these examples just demonstrate how van der Waals interactions are important from simple noble gas dimers up to very large, potentially astronomical scale objects. But let me now go back to Earth and ask a very simple question: how can we understand van der Waals interactions between 2 spherical atoms, right? That's the starting point, and this provides us with a textbook picture of van der Waals interactions. So let us assume that you have 2 spherical atoms, A and B, and because these atoms have spherical electron density, think of something like 2 argon atoms, for example. In classical electrostatics, you would have absolutely no interaction between these 2 objects because they possess no permanent multiple moments. They don't have any dipoles, any quadrupoles, and so on. And so the interaction energy should be 0. But of course, we know that reality is not classical, but it's quantum. And so in quantum mechanics, because vacuum is a quantum object, and if you put protons and electrons, for example, an argon atom, into vacuum, you would generate fluctuations. And these fluctuations of vacuum can be mapped to an atom, and we can say that at every point in time, so instantaneously, an atom has an induced electrostatic moment. In first approximation, it would have a dipole moment, which I show you here. So effectively, you can say that there is more electron density on one side of the atom than other side of the atom. Now, of course, if you integrate over time, you take the limit of infinite time, the atom would have a spherical electron density. But at every point in time, there is a fluctuation on the atom. And so this will happen to atom A, of course. You would have an instantaneous dipole moment on A. You would have an instantaneous dipole moment on B. And these instantaneous dipole moments would, of course, correlate. And because of this correlation, there would be an effective interaction between A and B that scales with the distance r between the 2 atoms. If you do this now beyond the conceptual model, you use perturbation theory, you can derive this effective interaction, which we now call the van der Waals interaction in second order perturbation theory, as this term here. It's a 6 coefficient for two atoms AB divided by the distance to the power of 6. The distance to the power of 6 in the simplest conceptual way you can understand as a dipole which scales as r cubed on atom A, a dipole which scales as r cubed on atom B. You have a product of these two dipoles and you get r to the minus 6 here in the denominator. Now the coefficient here can be derived again in second order perturbation theory by the so-called Casimir-Polder integral, and essentially it scales as a product of frequency dependent polarizabilities of atom A and atom B. And a frequency dependent polarizability is essentially quantity which describes these time dependent fluctuations on atom A and B induced by 0-point energy of the quantum vacuum. This function is in principle very simple because we write it as a function of imaginary frequency, so we make a Fourier transform from time to frequency. We go to imaginary frequency and it becomes a smooth function over which you can integrate, and if you can calculate this very accurately, you can compute van der Waals interactions for two atoms. Are there any questions up to now? Yes, please. So again, the simplest way to think about this is that you have a dipole on every atom, and a dipole scales as r to the minus 3, essentially, for every atom. And there is a product of these instantaneous dipoles, r to the minus 3, r to the minus 3, which gives you a total r to the minus 6. In other ways to think of a second order perturbation theory formula that Hardy had in his talk, where you have a dipole matrix elements and squared, and essentially every dipole matrix elements is r cubed, so squared you get r to the minus 6. This is the nature because vacuum is a quantum mechanical object that has a 0-point energy. So you have always exchange of virtual photons between the atom and the vacuum. Right? Even if you put a single charge in a vacuum, right, you would have polarization of that charge because you polarize vacuum. Right? I mean, vacuum is not empty.
Yeah, I know that.
Sure.
Yeah,
exactly. That's the simplest way to understand van der Waals interaction. So these fluctuations come from the fact that the vacuum is a quantum mechanical object which polarizes your atom. In this case, we only talk about polarizations of electrons, right? The nuclei would be also polarized, but the nuclear polarization is a much smaller quantity than the electronic polarization because the excitation frequencies are much higher.
Yeah, so this polarizability is frequency dependent. What kind of frequency?
It's right, this polarization would be time-dependent polarization, right? So you make a frequency integral, so you make a Fourier transform from time to frequency. Yeah, it's just a Fourier transform from time to frequency.
How can you extract these alpha parameters or model them?
You can calculate them from perturbation theory, what Hardy essentially explained in his talk. I will show this a bit later, how you can do it. Yeah. Yes? It's a ground state property. It exists in a ground state of an atom, but the exchange of photons, this quantum vacuum, right, makes it essentially, when you write it in perturbation theory, depend on all the excitations of an atom, right? So it exists in a ground state. The atom doesn't need to be excited, right? But because quantum vacuum is another quantum object with which the atom interacts, right? Effectively, it's a property that depends on the excitations of an atom. So it would exist in the ground state correlation energy of an atom, right? But in principle, to calculate it, you need to be able to access all the excited states of an atom. So in order to calculate these quantities here, the frequency-dependent polarizabilities, the simplest way to do it, or the practical way to do it, is to actually know all the excited state of an atom or a molecule. So because of this quantum mechanical nature of van der Waals interactions and all these instantaneous fluctuations that always happen, it is a ubiquitous interatomic and intermolecular interaction. the van der Waals interactions often scales, it always scales with system size, and it frequently scales in a non-linear fashion. So it's not just purely additive between all pairs of atoms, but it can scale in a highly non-linear fashion depending on the system size, on the polarizability, on the dimensionality, and so on. And often, van der Waals interactions makes a significant contribution to binding energies between atoms, surfaces, molecules, and so on and so forth. And that's why it's an important component of the binding energy, and so that's why it's important to treat it accurately. So up to now, I gave you a textbook, a theoretical picture of van der Waals interaction, and the question is, well, is it the right picture? And it turns out that it is the right picture, and you can actually prove this experimentally for two atoms. Before 2013, we didn't actually have an experimental proof that van der Waals interaction exists for two atoms. But in 2013, as a result of this paper, we now clearly know that this is the case. So measuring van der Waals interactions between two ground state atoms is hard, because the interaction is extremely small. So if you take two argon atoms, separate them by a distance of, say, 10 angstrom, the interaction is about 0.01 milli-electron volts. It's a very small number. However, if you have a Rydberg excited atom, so essentially you excite an atom to a very highly excited Rydberg state, the polarizability of that atom scales as n to the 7, where n is the principal quantum number of the Rydberg state. And the C6 coefficient that I've just described scales as n to the 11th. So the scaling is so steep that if you have a highly excited Rydberg state, the C6 coefficient is very large, and now it becomes experimentally actually measurable. So that's exactly what was done, what was accomplished in this paper. So people trapped two atoms in essentially optical traps, made an excitation, a controlled excitation to a Rydberg state, and then actually they were in an interference regime, so they controlled the pump probe lasers that they applied to the system, and by being in that regime, they could actually extract the van der Waals interactions from their measurements. What they got is this. So you have three different Rydberg states. In this case, these are, I think, rubidium atoms in a 53rd, 62nd, and 82nd Rydberg state. So n is equal to 53, 62, 82 here. And in all cases, essentially, if you look at this plot, you realize that at large distances, the interaction scales as r to the minus 6, as you would expect. And at short distances, you have higher order contributions, which come from higher order multipolar moments, the dipole quadrupole contribution, and so on and so forth. And so this is all expected, and it really provides an experimental proof that van der Waals interactions exist, even at very fundamental diatomic level. Now going beyond dimers, if now we would like to calculate van der Waals interactions for this kind of systems, large proteins or molecules adsorbed on surfaces, in principle, we need to solve the Schrödinger equation exactly. There is in principle no way to sidestep this solution, because van der Waals interactions now involves many electrons of this system or that system interacting over, in principle, all in the involved length scales, which in this case would be tens of nanometers. And in principle, we need to have the wave function for all the electronic degrees of freedom and all the nuclear degrees of freedom. So we've not even said that we can apply the Born-Oppenheimer approximation yet. In reality, of course, we often apply the Born-Oppenheimer approximation, so we only think about the electronic wave function because the nuclear polarization is much smaller compared to the electronic polarization. And of course, we need to take additional approximations because, as Hardy have told us, we cannot really solve the full many-body problem for all the involved electronic degrees of freedom. So what we do in reality is we use some approximate method. We have heard already about density functional theory and certain wave function based methods, but in principle, of course, you can start much lower. You can use an empirical potential, so-called force field, which has no explicit electrons whatsoever. Right? You can say, well, there are certain interatomic interactions between all my atoms because I coarse grain my electrons and I just represent them as forces acting on atoms. And in the Born-Oppenheimer approximation, you are allowed to do this due to the Hellman-Feynman theory. Now, the problem is deriving those potentials for realistic systems is difficult, and there is a wide range of such potentials in the literature. And so in principle, we would like to conserve some quantum mechanics at least. We can do this with semi-empirical methods. We can do this much better with density functional theory, which is in principle exact, but in practice we need to use semi-local or hybrid functionals. We can go beyond. We can include explicitly electronic correlations with wave function-based methods. You've heard already about MP2, about random phase approximation. You will hear more about quantum chemistry at the couple cluster level later in the week. And also in principle, we know how we can solve the Schrödinger equation exactly with so-called full configuration interaction approaches, where we construct an expansion of the wave function in terms of the ground state and all the excited state determinants. We determine variation in the coefficients in front of those determinants. And in principle, this would amount to the exact solution of the Schrödinger equation as long as we include all the relevant determinants. Now, as we go up here in this hierarchy, we improve the accuracy, reliability, and predictive power of our calculations. But of course, there is a big price to pay, because typically computational cost increases often exponentially. At this level, it's an exponential scaling. Here, it's very high power law scaling in terms of number of electrons. But also, there is another very fundamental problem. As we go up in this hierarchy, we lose conceptual understanding. We get wave functions which are extremely complex, but where is the conceptual understanding which we have at those levels? So in this picture, when we have complex electronic systems with many electrons, what we would like to achieve is some kind of synergy between density functional theory, at least, which describes things with a three-dimensional electron density, and wave function-based theories, which include electronic exchange and correlation effects explicitly. And that's what I will demonstrate in my talk, how we can achieve this in a context of van der Waals interactions. So as Hardy already said, density functional approximations, so-called DFAs, are quite solid starting point for our developments. They're very good because they can treat covalent bonds quite accurately. They can treat hydrogen bonds, strong hydrogen bonds, at a quite okay level, and they include a lot of electronic structure effects already in them. But of course, there are problems. So what we do in density functional theory is we coarse grain from a wave function, which is a 3 n-dimensional objects for n electrons, to just a 3-dimensional object independently on the number of electrons of our system. And we pay price because we construct all the non-trivial quantum mechanical many-body effects with approximating from the electron density. We can use the local electron density, the LDA approximation. We can use the gradient of the electron density with GGA approximations, or the Laplacian of the electron density using the meta-GGA approximations, and so on and so forth. But all of these approaches are semi-local. So if you have two fragments of electron density, as I had on my first slides, right? You have atoms A and B, and you separate them as a function of the distance. All of these functionals will give an interaction energy between these two objects, which decay exponentially with distance. Because density overlap decays exponentially. But we know from quantum mechanics that this is wrong. The power law, so the interaction should decay the power law, not as an exponential function. So that's a big problem, and that means that all semi-local DFAs lack long-range correlation, and therefore they lack the correct description of van der Waals interactions, even qualitatively correct description. So let me demonstrate this again on a simplest example of a prototypical van der Waals dimer. So in this case, this is an argon dimer. So what I'm showing you here on the left-hand side is the interaction energy. So the interaction energy of this dimer, so it's the energy of the dimer minus twice the energy of an atom as a function of interatomic distance. And my reference here is this red curve. This is so-called couple cluster method with single, double, and perturbative triple excitations, which for this particular system is essentially the exact solution. So this is my exact solution in red. And here I have different curves which correspond to different exchange correlation functionals. Here is the LDA, which you heard about in the last talk. Here is the PBE. Here is the meta-GGA TPSS functional. And here is the Hartree-Fock solution. So Hartree-Fock has no binding because it has no correlation. And different approximations to the exchange correlation functional give me arbitrary numbers, essentially. So I can get solutions for the equilibrium position anywhere from here to there. So I can overestimate by a factor of 3. I can underestimate by a factor of 2, right? It seems arbitrary for this system. But there is a very systematic behavior if you look at the long range distances. So I now zoom into this range from 4.4 to 5.4 angstrom, and now I show you exactly the same plots but zoomed in this range. And what you see here is that while the exact solution, the coupled cluster method, decays as r to the minus 6 in terms of the distance, as it should, all the functionals decay exponentially with distance. And that's how they should decay, because the overlap of electron densities decays exponentially, right? So then, if you take this into account, then even if your functional overbinds at short distances, it will always underbind at large distances, and so you need to somehow account for that. You need to add that part of the long-range correlation energy or van der Waals energy to any semi-local functional, independently of its behavior at the short range. Now, going beyond two atoms to more realistic systems, what are the failures of DFAs when it comes to van der Waals interactions? So typically, if you try to take your favorite semi-local density functional and calculate intermolecular interactions, you will find that the equilibrium distance of your molecules are overestimated by as much as few angstrom. Many molecules and crystals are even unbound. So if you take a benzene dimer, which is another prototypical van der Waals system, the reference calculation, this is quantum chemistry calculation, tells you that it should be bound by 2.6 kcal per mole. So the binding energy is minus 2.6 kcal per mole. At the PBE level, at this equilibrium geometry, you get 1.9 kcal per mole. So this is, of course, a qualitative failure, right? You get an error of about a factor of 3 in a PBE function. If you try to optimize the geometry, of course, it would fly away, right? It would not even bind in a PBE functional or any other semi-local functional for that matter. Also, if you try to study large molecules adsorbed on surfaces, so if you try to study benzene or a larger molecule on a metal surface, let's say, you would also not find any binding. It would fly away. While experiments clearly tell you that these molecules should be bound. They be essentially wet surfaces, right? Essentially all organic molecules, or most organic molecules, should wet surfaces. So this is clearly a disaster, and something has to be done to relieve this disaster in density functionals that we use. And of course, people have thought about this, and they have realized this quite a long time ago, and at least since the turn of the 21st century, since 2000, people have started working on this problem. How do we include van der Waals interactions in approximate density functions? So there is a wide range of them, and I cannot really describe all of the existing approaches, so I recommend you these two reviews that have been written over the last few years, one by Klimesh and Michaelides, another one by my group, where we have described the state of the art at this point in time. But this is a field that is moving forward quite quickly, so even today there are new approaches being developed every time, simply because the problem of treating van der Waals interactions is a very complex one, and it's a very important one. It really has relevance in physics, biology, chemistry, material science, and so there are many methods being developed still, I would say, as we speak. So the idea is in principle very simple. So you take your exchange correlation energy, right, and you take any given semi-local function. So you have an exchange energy which you can describe as with a GGA functional or exact exchange, like Hartree-Fock, for example, plus some semi-local correlation which can be described with an LDA or a GGA functional or a meta-GGA functional, and you add an explicitly non-local term. Now this is new physics, right, because there is no non-local terms here. There's only density-dependent terms which only use information about the vicinity of a given atom in a density, of a given point of the density, right? But we now add an explicitly non-local term. So this can be done in multiple ways. You can have a functional that depends on 2 points in space explicitly on point R and point R prime. This has been done by Langrest, Lundquist, and collaborators. You can, in the context of plane wave codes, you can, for example, use so-called modified pseudopotentials which mimic van der Waals interactions as an attraction between a nucleus and an electron. You can parameterize empirical functionals, such as meta-GGA functionals. This has been done by Truller and collaborators. You can put a very flexible functional form. You can fit parameters. You can describe mid-range correlations. You will never get long-range correlations because your functional is still semi-local. Or you can use this kind of approaches where instead of using points of the electron density, you are using atomic fragments to define van der Waals interactions. This can be pairwise interactions or beyond pairwise interactions, and many people have developed such kind of approaches. So I will now go and explain some of these approaches in a bit more detail so that you are aware of the state of the art in this field. So let me start with the Langres-Lundquist functional, which was a very important development in the field, and they have proposed two different approaches. The original one in 2004, so-called VDW-DF functional, and then they've revised their functional in 2010, and this is called VDW-DF10. So the idea is again simple. So you write the exchange correlation energy in this way, and you have to essentially model the non-local part of the correlation energy. So what they've proposed is that you can write the non-local part as this non-local integral. So essentially you integrate over all points R, all points R prime, of the density at point R, the density at point R prime, and the van der Waals interaction is propagated by a kernel, which again depends on densities and gradients at point R and R prime. So this is a very simple formula. The key is how you derive the expression for this kernel. That's not easy. It has taken them quite a number of years to get to this point. But the idea is that in particular in their original approach in 2004, they proposed that you can use a REF-PBE exchange as the semi-local exchange functional because it doesn't bind noble gas dimers. You can use LDA as a local correlation, and there were no free parameters. So it was a truly non-empirical functional which included non-local correlations. The error in C6 coefficients, so these are the dipole-dipole coefficients between two atoms, were about 20%, which was very, very good for the time. Now, over time, they realized by doing calculations on many systems that the accuracy of the whole functional was actually not satisfactory compared to other competitive approaches. And so in 2010, they decided to revise the definition of the kernel and the definition of semi-local functionals. They changed the exchange functional. They introduced two parameters in the definition of the kernel. And essentially, the other problem was that they actually increased the error in the C6 coefficients. So they essentially could describe better middle range correlations, but the non-local correlations or the long range correlations became worse. Now that improved performance on small molecules, but it didn't improve performance overall. Now, what are the problems here? So if you look at the original formula, this formula here, all this formula is doing, it's an explicitly non-local formula, but all it's doing is correlating 2 points in the density, at point R and at point R prime. So essentially it amounts to a local approximation for the polarizability, and you only compute pairwise density-density interaction. So you don't include any of the quantum mechanical many-body effects in the interaction between electron densities. So this is a big approximation because the polarizability and the C6 coefficients are non-local quantities by themselves. Because if you think about the polarizability, right, it's essentially proportionality between a dipole moment which is induced on a molecule or a material by an application of an external electric field. So polarizability is a tensor quantity because it's a relation between two vectors. Polarizability is a vector, electric field is another vector, right? So it's a tensorial anisotropic quantity. In this case, and it's also very non-local, right? It's a global change of a dipole moment to an application of an external electric field. In this case, you make a local approximation for the response, or for the polarizability, because you assume that every point in density here has its own local response, and it doesn't see anything else in the system. And this is nicely actually summarized in this paper by Dobson and Good. So another type of methods for including van der Waals interactions are so-called interatomic methods. So here the idea is you don't explicitly resolve every point in the electron density, but you find an interaction, you define an interaction in another coarse-grained way where you treat atomic fragments as your essentially fundamental entities instead of points in the electron density. This allows you to achieve much more efficient methods, and also, as I will demonstrate, typically they're actually more accurate. So here the idea is you represent again this non-local part of the correlation energy in this way. So you write it as a sum over all pairs of atoms in a more simple approximation. The first term would be cis6 r to the minus 6. Then you would have a dipole quadrupole C8 r to the minus 8, and so on and so forth. So you do a multipolar expansion of the interaction, and you multiply all of these terms by functions that saturate the interaction at short distances, right? This multipolar expansion would diverge at short distance, so you need a function which actually brings the interaction to 0 at the short range, or to some finite constant at the short range. Now, if you look at this expression, then you need two parameters for every atomic pair. You need a van der Waals C6 coefficient, and you need a van der Waals radius, which defines how you saturate the interaction at short range in terms of the approach between two atoms. So clearly, if these two parameters are empirical, you have too many empirical parameters. If you have 4 different atoms, let's say carbon, nitrogen, hydrogen, oxygen, you would need 10. You have 10 atomic pairs, so you need 20 empirical parameters. This is clearly too much, especially if you want the whole periodic table. So frequently, these parameters were empirical before 2008, but since 2008, people have started to think how to derive all of these van der Waals parameters from the electronic information that you have in DFT calculations. So just to briefly summarize the evolution of these different methods, Stefan Grimme was really one of the first people to propose useful methods, useful interatomic methods that you can use to correct semi-local density functions. So he has developed a variety of methods from so-called D1 to D2 to D3, so from 2004 to 2010, which provided a parameterization of van der Waals parameters for many elements in the periodic table. But the actual concepts he used are quite highly empirical, and there are some very ad hoc approximations in the way that the parameters are defined. So it's a very empirical approach to derive van der Waals parameters, although of course as time goes by, in principle some of the empiricism is reduced. Other people, for example, the group of Pavel Hobza, in particular Jurichka and others, have provided accurate parameterization for organic molecules, which had better theoretical grounds, but they were still very empirical. Then, about 2005 to 2008, both the group of Axel Becke and Erin Johnson, who was a PhD student with Becke, actually presented a way to derive the C6 coefficients and van der Waals radii from Hartree-Fock or DFT orbitals. So they derived an orbital functional for polarizabilities and van der Waals radii. This clearly reduced empiricism, but still had errors of about 20 to 40% in the long range C6 coefficients. C6 coefficients depend on the polarizabilities, and polarizabilities are hard to calculate because you need all the excited state spectrum of atoms. So it's not easy to represent them as functionals of electron density or of occupied orbitals. Now, what we did in 2009 in collaboration with Matthias Scheffler is actually derive a way to define C6 coefficients and van der Waals radii as pure functionals of the electron density without requiring any information about the orbitals. So the key here was that we can actually calculate very accurately C6 coefficients and polarizabilities for free atoms in vacuum, and then we can extend this approach using this reference data for free atoms by using the electron density of our system, and I will demonstrate in the next few slides how we do it in practice. This allowed us to obtain C6 coefficients without any empiricism for molecules and materials to an accuracy of about 5%. Now I have here dots, which means that, again, this field is not dead. The field is very alive, and many people are working on improving this methods constantly. Just, I think, 2 weeks ago, there was another publication from Stefan Grimme on so-called D4 method, which extends it to ionic systems, and people are still working quite a bit on improved non-local functionals and other approaches to van der Waals interactions. So again, we have two different methods. We have non-local functionals, we have interatomic approaches. And the question is, what is missing in interatomic approaches compared to non-local functions? Well, if you think about the physics and the concepts that go in these interatomic methods, the missing bits are essentially exactly the same as in non-local functions. So what you do here is you assume that you have atomic fragments of electron density from which you use to define van der Waals parameters, but you're only using semi-local information of the density. So you still take essentially a local approximation, a semi-local approximation to a polarizability of an atom. It can be much more accurate than in non-local functionals because you are using some reference information for the free atoms, but you're still essentially assuming that the polarizability can be partitioned in an additive way in your system. This is a big approximation. It means that you are missing electrodynamic response effects for fluctuating dipoles. And the second bit that you are missing are the non-additive many-body van der Waals energies beyond the pairwise approximation. So you're still summing over pairs of atoms, which means that many-body effects such as axial or Taylor three-body effect and high-order effects are missing from your pairwise approximation. So how can we go beyond that and actually really include the quantum mechanical many-body nature of electronic correlations and van der Waals interactions in our approaches? Well, what we have to realize is that if you have a system of atoms or electron densities, we can, in the first approximation, we can assume that every fragment in our system, right, this fragment can be point in the electron density or it can be an atomic fragment, is a fluctuating dipole. And there is an electric field which it causes, right? And the origin of the dipole are again quantum mechanical fluctuations, right? 0-point energy of vacuum. And so in the simplest approximation, we now say, well, we associate a fluctuating dipole to every part of our system. And we want to know how atom A and atom B interact in this system of fluctuating dipoles. Now, of course, in the first approximation, these dipoles are independent, right? So every fragment is a fluctuating dipole, and every fragment doesn't see all the other fragments. This would be an independent particle picture. But of course, we know that this is not the correct picture. Atoms and electrons, right, interact between themselves, and they interact through Coulomb potential, and the Coulomb potential modifies the local description of our system, or independent description of our system, and makes it collective. And this introduces many-body quantum mechanical effects in the correlation energy in general and in van der Waals interaction in particular. So what we need to do in order to understand how atoms interact is essentially compute the so-called linear response density-density or density-density linear response function of our electronic system. And we can do that by introducing this trick that was already mentioned by Hardy. So we use the so-called adiabatic connection idea, where we can adiabatically switch the Coulomb potential from this form, 1 over R1 minus R2, to this form, where we introduce a parameter lambda, which can scale from 0 to 1. So if lambda is 0, then there is no Coulomb interaction in our system, right? We have just a system of independently fluctuating dipoles. But as we scale from 0 to 1, we introduce correlations, we introduce interactions between our independently fluctuating dipoles. And this introduces non-trivial effects in interaction energy. Right? This introduces two different effects which are crucial. They are both many-body effects. The first one is that we have electrodynamic Coulomb response in our system, right? Which means that every oscillator is not independent, but it's oscillating collectively with all the other ones in phase and out of phase, right, at all different frequencies. And the second one is that the interaction between A and B, right, is just one part, right? You have to sum interactions between A and B, between A R1 and B, A R2 and B, and so on and so forth. So you have 3-body interactions, 4-body interactions, 5-body interactions, 6-body interactions, to infinite order in principle. So how can we do this with an actual formula? Well, this was already also mentioned by Hardy, so we can do this with this formula, which is so-called adiabatic connection fluctuation dissipation theorem, which is a way to write a correlation energy in this case. So this is an exact expression for the correlation energy of an arbitrary electronic system written in terms of this linear density-density response function. So this would be equivalent, if you had the exact density-density response function, this would be equivalent to solving the Schrödinger equation exactly. Now, unfortunately, we don't know how to compute this object exactly, so we need to model it. So the formula is in principle very simple, right? You have the integral of a frequency, right? This is exactly the same frequency that I had in on my first slide. You have to integrate over this adiabatic coupling constant lambda, and you have to integrate over R1 and R2, where R1 and R2 is any spatial positions in your system. You have to integrate this difference between a response, an interacting response function, and non-interacting response function multiplied by a Coulomb potential. So if you can do that, you get an exact correlation energy. So the only issue now is how you obtain this function here and that function there. Before I tell how we do it for dipoles and how we can compute many body van der Waals interactions, let me just mention what new insights you can get once you can compute the fully non-interacting polarizability of different materials. So I would like to mention an example of carbon nanomaterials. Because typically when people model such carbon nanomaterials and they want to, for example, study self-assembly behavior between nanotubes and fullerenes, typically it is assumed that van der Waals interaction can be just described in terms of C6 coefficients, sums over all pairs of atoms over C6 coefficients, which depend exclusively on hybridization states. And they don't depend on the geometry and dimensionality of the system. And so typically what people do is they use coefficients in this order between 20 and 30, which amount to essentially extrapolations from the dielectric function of graphite. So in order to see whether this approximation of just hybridized hybridization dependent C6 coefficient is correct or not, we actually now solve the system of interacting oscillators. And from the system, once we solve it, we can get the fully interacting polarizability. We can obtain a fully interacting C6 coefficient. We can divide by the number of atoms that we have, and it gives us an effective C6 coefficient for different materials. So if we do this for diamond and graphite, which are three-dimensional systems, we get values of C6 coefficients which are around around the numbers that people are using in the literature. But if you now go to graphene, which is a two-dimensional material, so you break three-dimensional symmetry and you introduce dimensionality by having a two-dimensional material, you now realize that your C6 coefficient is not here, but it's actually by an order of magnitude larger. And that's because all electrons in graphene can only polarize in plane, right? There is nothing out of plane, so there is no polarization out of plane. There is only polarization in plane, and this polarization is extremely large. And because of that reason, your C6 coefficient scale non-linearly, and it's by an order of magnitude larger than in standard three-dimensional materials. If you apply this to a wide range of other systems, one-dimensional nanotubes, nanoribbons, fullerenes, you see that in all of these cases, the van der Waals C6 coefficient scale in a highly nonlinear fashion, and they can be anywhere between 20 and 160. So again, it's an order of magnitude change of the C6 coefficient due to a simple dimensionality and geometry effect beyond any chemical hybridization. So these are long-range many-body effects that make van der Waals interactions non-additive and also enable you to actually control self-assembly of these systems by playing with the dimensionality and geometry of the different carbon nanostructures. Now let me finally, I think I have 5 minutes, right? So just to briefly mention that this theoretical picture that I just presented you is not exclusively a theoretical picture. You can actually make experiments to demonstrate that van der Waals interactions are very long range. Such experiments have been done, for example, in a group of Karin Jacobs in Saarbrücken, where they have observed how van der Waals force scales as a function of a thin film size of silicon dioxide that you grow on top of a silicon surface. And they have observed that the saturation of the force occurs only when the thin film thickness exceeds 100 to 200 angstroms. So again, it's 10 to 20 nanometer range of the van der Waals interaction, which is what we observe in our calculations as well. So experiment, in this sense, agrees with theory that van der Waals interactions are very long range, much more than just a pure sum over pairwise sum of C6 coefficients. Okay, so now let me describe in the last 5 slides how we can actually calculate the system of fluctuating dipoles and how we can obtain many body effects. So again, just let me remind you that the conventional approach to computing van der Waals energy, which have been worked on by many people, some of them mentioned here, is this one. So essentially you break your system into fragments, you define the polarizability of those fragments in a local way or a semi-local way, and then you sum over pairwise interactions between all fragments of your system. If you think about where such approach is valid, well, for very small molecules, this is a valid approximation simply because their polarizability is not very non-local. You can represent it quite well by an additive approach. Also, if you have a homogeneous dielectric material, so for example, a noble gas crystal or even a silicon crystal, the polarizability is very localized. So in principle, such an approach could work for homogeneous dielectric materials or for small molecules. But realistic systems, many-body systems, are much more complicated. And you need to include essentially the full many-body nature of polarization and the correlation energy. And the way we have proposed how to do it is so-called DFT plus MBD method, where again DFT is density functional theory and MBD stands for many-body dispersion. It's nothing else than just essentially a system of dipole quantum harmonic oscillators, which in the dipole approximation can be fully characterized by a static polarizability and an effective excitation frequency. This model has been used quite a lot in the literature, also in the context of van der Waals interactions, but until we started working on it, there was no way to actually define these two parameters of the oscillators from first principles. So we have provided such a parameterization with our TS work in 2009. Essentially, we found how to parameterize a system of dipolar oscillators from the self-consistent electron density of your molecular material plus reference numbers for free atoms in a periodic table. Once we have that parameterization, this allows us to obtain a system of oscillators. I would call them hybridized oscillators. Then you need to solve a short-range electrodynamic screening equation because you are working exclusively in the dipole limit. You need to include Coulomb effects at the short range. And finally, once you have the system of screened and hybridized oscillators, you can couple them with a long-range dipole potential, and you can use the adiabatic connection formula, or you can directly diagonalize the Schrödinger equation with the dipole potential, and by diagonalizing the Schrödinger equation, well, the interacting Hamiltonian essentially, you can obtain the long-range correlation energy, which includes all many-body effects to infinite order. What this gives you is essentially an integration or a synergy between a density functional theory approach and a wave function-based approach. You have a wave function for the oscillators, which is a coarse-grained wave function, which describes dipolar oscillations, dipolar many-body oscillations of your system of oscillators. And you have a density from your DFT calculation, which parameterizes this system of dipolar oscillators. So it's a true, I think, handshake between a density functional theory and wave function-based theories in a dipolar element. If you measure the accuracy of the polarizability sense of 6 coefficient, the MBD method gives you accuracy of about 7%. It has a negligible cost compared to density functional theory. You can do MBD calculations for up to 10,000 atoms. It scales cubically, and the matrix size is much smaller than the Kohn-Sham matrix sizes that you treat in your calculations typically. Now, there is a catch, and the catch is that there is a single adjustable parameter which is empirical and that you need to obtain in order to couple a long-range correlation energy that you get from the MBD Hamiltonian to your semi-local function. This parameter is obtained for every functional, and it essentially describes how it measures how many semi-local correlations are there in your semi-local function. Just to give you the results which we have for all the methods I have described in my talk. So this is the performance of different approaches for gas phase intermolecular interactions on so-called S22 database of intermolecular interactions. Some of the systems are shown here, such as benzene dimer, uracil dimer, methane dimer, and so on. You can see that there's a wide range of performances. For example, MP2, which is the method that Hardy talked about, performs not so well. RPA performs much better. And in the end, MBD plus a good hybrid functional actually gives you an accuracy of about 4% in intermolecular interactions. If you go to much larger systems, you find that the importance of many-body effects grows significantly. So this is just the saturation of the van der Waals energy as a function of perturbation theory. So here we have 2-body interactions, 3-body interactions, 4-body interactions, and so on. If you look at very large systems, such as the difference between A DNA binding and B DNA binding, or this DNA ellipticin binding, so this is a drug molecule, you find that you need to go at least to about 8-body interactions to convert your energy to chemical accuracy, 1 kcal per mole. So this means that as you increase the complexity and reduce the dimensionality of your system, the effect of many-body interactions actually propagates to much larger orders of perturbation theory. With these theories, you can also go from small molecules to large molecules and to molecular crystals. So here I show you the mean absolute relative error in percent compared to high-level quantum chemical calculations or experimental numbers for molecular crystals. And as you can see with the pairwise theory, your error increases significantly from small molecules to large molecules and molecular crystals. So you go from about 10% to about 30% error. But when you include many-body correlations, these are these 2 bars using a PBE functional and a hybrid PBE0 functional, your error essentially stays constant in about 5 to 7% error for all systems from very small ones to very large ones. So this just demonstrates the flexibility of the approach and also the transferability to larger and more complicated systems. Okay, let me go to my last slide. So just to summarize, I've presented a hierarchy of atomistic approximations to van der Waals interactions, so to van der Waals correlation energies. I've told you that there is an exact approach, so-called adiabatic connection fluctuation dissipation theorem, which can be written in a very condensed form like this. But unfortunately, calculating this linear response function that is involved in this approach is very costly for all the explicit electronic degrees of freedom. For this reason, most calculations in the literature now employ these 2 different approximations, either non-local 2-point functionals or fragment-based approaches to van der Waals interactions, which essentially have different formulas, but the conceptual physics in all of them is exactly the same. But I told you that in principle we can go beyond these pairwise approximations to a fully many-body approximation by rewriting the expression for the response function not in terms of electrons but in terms of harmonic oscillators. And by doing so in a dipole approximation, we can essentially conserve the many-body nature of the correlation energy, but we can calculate it in an efficient and practical way for thousands of atoms. I leave you with a list of reviews which my group has written on this topic. It's a field which has been exploding over the last many years, and people constantly write reviews, I think, every 1 or 2 years. This is just not a comprehensive list. I've provided a list of other reviews by other groups during my talk. And if you just want a brief reading, this is something I would recommend. And thank you very much for your attention.